Hello, my name is Bob McKillop, and I'd like to tell you about our current effort to significantly expand the countermeasure modeling capability of the Navy. The title of our work is Extended Domain Chaff Release Modeling for Fixed and Rotary Wing Aircraft. I'll describe for you a software development project that has combined a best-of-breed unsteady aerodynamic model for aircraft with a validated particle tracking model to generate time-accurate predictions of chaff countermeasure release scenarios. Those simulations can provide data for signature analysis and support advanced tactics and doctrine development to improve aircraft survivability. This effort is actually an evolution of an original Navy topic on an advanced icing accretion modeling and sensing for the V-22 Osprey, in that a similar combined aerodynamic flow field calculation and droplet trajectory analysis were used to compute icing growth rates on that aircraft in its flight profile. But first, let me tell you a bit about our company and our capabilities. Continuum Dynamics Incorporated is located in Ewing, New Jersey, and was founded in 1979. We have 25 employees and specialize in aircraft analysis, design, modeling, and simulation, with a particular emphasis on computational aerodynamics. We have commercial software codes that are used by both government and industry for engineering, design support, and research, having licensed them to all of the major primes, as well as support contractors and startups. The aerodynamic analysis tools have been used in aeromechanical design support, acoustic predictions, store and particle release simulations, loads and performance assessment, and have been integrated into manned flight simulators for rotary wing and fixed wing aircraft. CDI's contributed engineering, design, and analysis solutions in the aerospace, mechanical, and nuclear engineering fields since its inception in the late 70s. Our Navy effort here leverages this past experience with current Army-funded experimental work to further expand our particle modeling to support chaff countermeasure release simulation. The Navy desires to protect their aviation assets through continuous improvement in systems and methods for countering adversary threats that have ever-expanding capabilities. These improvements include gaining better understanding of the details associated with countermeasure release, such as transient behavior of chaff fibers following aircraft release and operational flight profiles that may include evasive maneuvers. Local flow effects on chaff immediately upon release can establish initial conditions on subsequent dispersion behavior that can lead to significantly different far-field signature properties. Thus, proper physical modeling of this interaction is crucial to a better understanding of the transient nature of the resulting countermeasure effectiveness and can support development of alternative release strategy and tactics for improved survivability. To appreciate how this improvement is possible, we have to first characterize the existing modeling technology available in this realm. Current chaff countermeasure models will typically represent the dispersion process using simple spatial growth models and data-driven transient growth rates extracted from actual release tests. The software used with these legacy models will incorporate static or steady-state aircraft wake flow fields that represent cruising flight conditions and thus have no transient modeling capability. The actual chaff cloud evolution is a dynamic process that responds to both changing aircraft wake structure and aircraft maneuvers, and thus can be influenced by flight parameters in its time evolution. But in order to simulate this behavior, one needs an accurate and validated flow field model that can drive the physics concerning the dispersion of chaff fibers following release. Several flow field domains govern the chaff cloud dynamics and include the near field regime, where the local shear flow dominates the initial behavior immediately upon release, a midfield zone near the aircraft where local vortices further modify the dispersion shape and cloud propagation, and a far field volume where local winds and the rolled up aircraft vortex pair are the primary flow field effects. The integration of these transient flow fields with the chaff countermeasures transient response has been coded into the countermeasures toolbox for MATLAB, described next. The countermeasures toolbox is a MATLAB-based software tool for modeling dynamic chaff release for maneuvering fixed and rotary wing aircraft. The toolbox includes CDI's CHARM free wake vortex model, or CHARM, is an acronym for Comprehensive Hierarchical Aeromechanics Rotorcraft Model. That represents the flow field from these maneuvering aircraft and performs a time-marching simulation of the chaff fiber dispersion from initial release through cloud expansion to settling in the far-field environment. Simulation data can be used for quick look analysis of signatures for the chaff cloud and the aircraft as part of the toolbox software, or it can be shared with existing DoD signature analysis software tools. The MATLAB environment allows for ease of problem setup and graphical visualization of simulation results, but the physics engine for computing the dispersion behavior can be exported for integration into other DoD countermeasures simulation assets. Aircraft model data needed for the weight calculation are lifting surface or rotor geometry, a simple vehicle panelization, and a nominal gross weight. Many models of current DoD aircraft are included in the toolbox. Aircraft flight profiles can be generated from a combination of parameterized maneuvers, from custom MATLAB functions operating on simulation data, or from actual flight test telemetry data for reconstruction of a test scenario. Multiple types of chaff may be selected, and launcher locations and ejection parameters can be specified in tabular form or physically adjusted via GUI interaction with the displayed 3D aircraft geometry. Signature analysis for a quick look assessment can be formed for both stationary and independently moving reference frames, such as on a seeker. This toolbox greatly extends the Navy's modeling capability for survivability analysis and can directly impact development and improvement of strategy and tactics in response to adversary engagements. The current Phase 2.5 software development effort is a 36-month program with 18-month base and option phases, and is now just starting the option phase. Initial baseline software delivery had the goal of collecting user feedback and generating interface documentation for use with DoD software assets. Navy Crane is the primary interface user, with additional support from NavAir. The option phase will include correlation and validation work using actual chaff release data, most likely from tests conducted at the Atlantic Test Range, with several more code update deliveries. Key features, advantages, and benefits of this software are shown on this grid in comparison with existing DoD software assets. The leftmost column of this chart shows the various features desired of a countermeasure simulation asset, which include the capability for transient analysis, the type of flow field model available, the physics model for the chaff dispersion, and the signature analysis assets. The top row of this chart shows the three categories of simulation tools. The first is a simple statistical model, the second is the current Navy time marching simulation tool, and the third is the countermeasures toolbox described here. The capability to model transient behavior is available for both the current Navy tools and the countermeasure toolbox, but the present Navy tools are limited to only calculating transient chaff cloud dispersion versus the toolbox capability for calculating a transient flow field during release. Flow field models for the statistical analysis typically just use ambient wind profiles, whereas time-marching Navy simulation tools presently incorporate aircraft flow fields for cruise flight conditions only. The countermeasure toolbox, however, can represent detailed flow conditions across several domains and capture transient maneuvering flight profiles for that maneuvering aircraft. Chaff cloud physics for the statistical models incorporate collective average properties, while the current Navy simulation tools allow for more distributed statistical descriptions of the cloud. The countermeasures toolbox include time-evolving covariance calculations for the chaff fibers for position, attitude, and velocity, supporting enhanced signature analysis of the results, such as polarization and Doppler effects. And finally, while the purely statistical models include some form of collective signature representation, the current Navy tools use a separate software suite for the signature analysis of the release event. The countermeasure toolbox provides some quick look analysis tools that help determine sensitivities of simulation parameters to computed signature, thereby allowing for iterative adjustment of flight profiles and release sequencing prior to export of the dataset to existing validated DoD signature software assets. So how do we transfer this software to the fleet? As mentioned, Navy Crane is the initial and primary user of this asset, as the development cycles are structured to iterate with their evaluation, testing, and integration activities with other DoD software tools. The CHARM flow field model may also be extended for integration with other existing Navy countermeasures tools for those users that do not wish to run the toolbox in a standalone mode. Further, model improvement will incorporate shaft release data from a separate Army contract to CDI, where controlled release behavior is recorded for a range of different onset and vortex flow environments. Extensions are underway to include additional models for thermal countermeasures such as flares and pyrophorics within the toolbox. And using companion flow analysis tools, future applications can include countermeasure release modeling for surface ships. The overall goal of the effort described here is to make the countermeasures toolbox a DoD-wide modeling tool that can simulate a variety of countermeasure releases from multiple aircraft platforms for all surfaces. Portions of the codebase may also be exported for use in existing DoD simulation tools to enhance the existing physics models for the countermeasures response and to replace the representation of the aircraft flow field with one capable of including aircraft transit and dynamic maneuvers. The potential exists for ongoing support through an IDIQ contract to expand the quick look signature analysis capability, provide support for surface ship countermeasure modeling, and operate in real time to support manned simulation engagement scenarios. I encourage you to consider how this improved countermeasure modeling tool can support your mission to enhance Navy survivability, and humbly ask that you contact us directly to discuss how we might help you. Our contact information is shown on this slide with physical and website addresses, and I can be reached via cell phone or email as shown here. I want to acknowledge our Navy sponsors, John Doyle and Brent Wagoner, both from Navy Crane, and thanks, of course, for your attention, and I hope to work with you in the near future.